Hello there, my name is Charles Wells Finance. Welcome to our first presentation on differentiation. I hope you are going to enjoy this presentation. We're also going to start very simple, and by the end of this presentation, I hope you'll be able to compute your own derivatives from basic principles. In this case, we're referring to the definition of derivative. So let's start this way. We look at this situation which we are all familiar with, which is where we've got a equation of a straight line which is equal to y is equal to f of x equals to mx plus c. So we know that if you're given 2 points on this line, we can calculate the slope of this line by using this formula. We say y2 minus y1 over x2 minus x1, which normally you can also abbreviate as rise over run. I hope you understand that if you are given a point on the curve of a function, always the coordinates of the points are x, comma, f of x. If we rewrite this expression in other terms, what we can do is we note that the difference from x1 to x2 here, we can denote it by delta x, what we call the change in x. So our y2, our x2, you can take it as x1 plus change in x. So from what we've said here, then this is y2, which is x1 plus change in x minus f of x1 over delta x, which is our change in x there. And again, we can now look at the numerator, which is here, which is f at x1 plus delta x minus f at x1 as change in the values of the function. Then we can write that as change in y. So then our gradient now is as follows. Now we note one important fact here, that this gradient of a line is actually a constant. And noting that the gradient here actually represents the slope of the line. So what we're saying is that the slope of a line is constant. But we know that in mathematics we don't only deal with lines, we sometimes work with general curves. Like for example, if we've got a curve like this, and we notice very clearly that if we look at the slope here and compare to the slope somewhere there, it's clear that they are very different. Actually, if we want to talk about a slope of a curve like this, we can only talk about the slope at a point, because there's no one slope for the whole curve. In this case here, the slope of the curve at this point is actually coincide with the slope of the tangent line at that point. I think you can see that if you've got a point here on the curve, on the red curve here, and on the tangent line, which is black here, and it slides like this, that point is slides here, it will experience the gradient of the tangent line. So what we're going to agree on is that the slope of a curve like this at a point coincides with the slope of the tangent line at the same point. What actually happens here is the situation like this. We've got the small segments here, and the dots there are trying to magnify the points. These small segments are segments from tangent lines. So what we can see clearly here, this tangent line here has got a different slope from that one there, and so on. So what actually happens is that the slope of a curve, general curve, changes from point to point. In other words, looking at this point here, we can say that the slope there is unique. In this case, it is the slope of the tangent line at that point. So as we move along the axis from point to point, the slope is going to change. So going further, we can look at the situation like this, whereby we have got the tangent line and a slope there, it shares with the curve. And if we draw a second line like this second line is going to have its slope, which we can represent this way. We know that now here we've got a point x0, so the change in x will be from there to there. So when we calculate this and the points there, this will be actually x0 plus change in x, comma, f at x0 plus change in x. So now, using this point and this point, and in this case, what we have, we've got point x0, comma, f at x0. So now, using these 2 points, you can calculate the gradient of a second line, which is given here. And then the tangent line can be represented by this equation, says y equals to m tan x. Now, we're indicating that this is the gradient of a tangent line plus c. If we wanted the slope of the curve at this particular point, we will talk of what we call the slope at an instant when x is equals to x0. So to talk about that, we need to look at a situation like this. What we have here, the grid line is the tangent line, and this equation is given there. And then we've got our second line, and the slope is given. So what we want to do here, if we slide this point along the curve here, we can see that the slope of the tangent, the second line, is decreasing. It is steeper here, less steep here, and even less steep here, and closer to the slope of the tangent line. So what we can see here, as we reduce change in x from here to there, we see that the slope of the second line, which I've denoted here as m sec, approaches the slope of tangent line. And then if we continue with this process until we get as close as we wish to x0 here, we will see that the change in x will be approaching 0. Otherwise, we are moving towards looking at the limit of this incremental quotient, which gives us the slope of the tangent line. Or we can see that if we pick any point, in this case, in which is not necessarily x0, and do the same process, the limit of this incremental quotient will always be the slope of the tangent line. So let's see where this takes us to. If we now pick a point, we've seen that this takes us to the slope of a tangent line. Then this kind of limit, we're going to call it, this kind of expression, which is here, we call it an incremental quotient. And then its limit, it gives us the slope of the tangent line. And since we say that the slope of the tangent line coincides with the slope of the curve at that point, so which means whenever we need a slope of a curve at a particular point, we're going to use this, and this takes us to the concept of a derivative at a point. So this is what we're going to look at. Now, if in this case here we use this incremental quotient to define the derivative as the limit of the incremental quotient as the change in x is turned to 0. So if we pick an arbitrary point x, and they will do this, what is going to happen is that we're going to get the slope of the tangent, so the slope of the tangent line, which coincides with the slope of the curve, and we're going to call this the derivative of the function at that chosen point. Now, having this, now we need to play around with this kind of a definition and see what we get. Let's look, for example, at a function f of x equals to 2x plus 5. I think because of this is a straight line, we can agree that the slope of this line is equals to 2. So then, and then we see also that this line passes through point 0, 5, and also it passes through another point like 1, 7. So we know that using the formula for calculating gradient, we can actually get this 2 by saying 7 minus 5, which is our rise, over 1 minus 0, which gives us 2 over 1, which is equals to 2. Now, if we want now to use that incremental quotient, let's take a change in x, which of course this change in x is taken to be different from 0. Then we calculate the limit of the incremental quotient as x is tending to 0, data x tending to 0, but different from 0. That will mean that we take f. Let's do that at a point like 1, 7. So say f at 1 plus change x minus f at 1 over in this case 1 plus change x minus 1. So we see that this takes us to the limit as delta x approaches 0 of evaluating this function at this point. We would get 2 brackets 1 plus delta x plus 5 minus 2 times 1 plus 5, this should be in brackets, over, in this case, change in x. Now simplifying here, we can see that this takes us to limit as delta x is approaching 0 of 2, multiplying here 2 times 1 minus 2 gets 0. Then we've got here 2 times delta x, and 5 minus 5 gets 0. Then we're left with 2 times delta x divided by delta x, and we see that this simplifies, and then we're left with the limit as delta x is approaching 0 of 2, which is a constant not depending on delta x. Then that is going to be equal to 2. And this is the what you can now call derivative of our function at point equals to 1, and we can see that it coincides with the gradient of the function what given. Then, so this happens with any point because the derivative of a line is a constant. Now let's take a different function like y is equal to f of x equals to x squared plus 2x plus 5. I hope you can note that we have got that function which you saw before in the previous example here. Doing the calculating the derivative of this function using the chemical equation, we'll say now f prime, which denotes the derivative function. In this case, we're going to take it at an arbitrary point x. Now it's a generic point x along the axis. So what would you do? We will say this is equal to the limit as delta x approaches 0. And then this, we're going to have x plus change x minus f at x over change in x. First of all, we're going to evaluate this separately here. We're going to say f at x plus change in x is equals to x plus change in x all squared plus 2x plus change in x plus 5. Simplifying here, you can see this is a perfect square, which is going to simplify to x squared plus 2x delta x plus delta x squared. Please here don't make a mistake of multiplying this x and that x. This is actually not x, it's change in x. So it stands on its own as it is there, plus 2x plus 2 change in x plus 5. Now, evaluating f at x is going to give us x squared plus 2x plus 5. Now, doing the subtraction, we're going to do it this way. Let's say limit as delta x is approaching 0. Now, if we subtract this expression from that, we see that this and that is going to give us 0. Then we also 5 and 5 are going to give us 0. Then we've got 2x here, and the 2x we're going to have 0. What we're left with there, we're left with 2x delta x as part of our numerator plus delta x squared plus 2 delta x there, 1, 2, 3 terms over delta x. Now, if we reflect briefly, you can see that if we evaluate this limit directly, we get the undefined expression 0 over 0, which you can never give as a limit to an expression. So what we do the usual, we factorize and see whether we can simplify to avoid this kind of undefined expression. So we've got limit delta x going to 0. We can see in the numerator we've got delta x as a common factor, so we take it outside the brackets here, and we're left with 2x plus delta x plus 2 over delta x. So we can see now that these two simplify to 1. Then we've got here limit as delta x is approaching 0 of 2x plus delta x plus 2. So now since we don't have any problem with this, then what we can do now, we can just evaluate the limit directly, and what we see, we've got 2x plus 0 plus 2, which simplifies to 2x plus 2. So now what we can now write is that if we've got a function here, y equals to f of x equals to x squared plus 2x plus 5. Its derivative is y. We can write this as y prime, or f at x prime equals to 2x plus 2. Now what we note here, because we're using, we just picked a generic point x, the derivative of the function is going to be another function in this case. But when we're dealing with the line, we saw that the derivative of a line, function y is equal to 2x plus 2 gave us a constant 2, which is actually also a function, but in this case a constant function. So now, what is the purpose of this function? The purpose of this function, if we choose a point, like let's say we know that this is a parabola. So if we choose a point like 1, which x equals to 1, we're going to have a point 1, comma, substituting here with 1 plus 2 plus 5, which is going to be 8. So this will be a point on the parabola. Now, if we evaluate this function at 1, then the value of this function, which is actually 2 times 1 plus 2, is going to be equal to the slope of the tangent line, in this case 4, at this point. So now, if I'm looking at these two functions as a pair, this function delivers gradients of this one at chosen points. So lastly, let's look at a very interesting example, which is this one. In this case here, we've got a function which is called f of x is equal to c, and you can represent it this way on a system of coordinates. So now, if we want to get the derivative, we'll do exactly the same thing, say f prime at x equals to the limit as delta x is approaching 0 of f at x plus delta x minus f at x over the change in x. Now, let's look at what happens to the graph here. So if we've got x here, and you can have another point there, which we call x plus delta x. But we see that if we evaluate this function here, the value of the function is the constant, and we evaluate it there, again, the value of the function is the same constant c. So we can take this as limit delta x approaching 0 of c minus c over delta x. So which means we're actually calculating the limit as delta x is going to 0 of 0 over delta x. Remember, we said delta x is only approaching 0, but is different from 0. So the answer to this will be equals to 0, because we're dividing here, we're dividing 0 by a number, and that will be, the answer will be 0. So what does this say? It gives us that the derivative of a constant function is equal to 0. And since we saw from the straight line in the beginning that the gradient was depending on slope, so which means that the measure of slope of a horizontal line is equal to 0. So whenever the derivative is equal to 0, we would understand that we are dealing with a straight line which is actually horizontal. And we note that at the same time that if we had a vertical line, let's say we've got a vertical line like this, then what would happen if we talk of changing in x from different points on the line? We'll see that the change in x will be always equal to 0 for a vertical line, and then the slope in this case would be, if we want to do something like this, it would have a change in the values of the function over 0, which is undefined, meaning the gradient of a vertical line is actually a defined entity. So up to this point, I hope you have seen how we can use the incremental quotient to compute derivatives, and I hope you can start practicing with this incremental quotient. I urge you to take your text and look at similar examples and compute derivatives until you feel you can master this kind of computation. Others, for now, I would like to say thank you for listening.